Hi, welcome to Sunil Maths tutorial, Galois Theory, class number 5. In this video, we solve some problems depends upon previous theorems, especially on Einstein's criteria and some another theorems. Let us see the first problem. We use Einstein criteria whenever to check the reducibility or irreducibility over the set of real numbers capital Q. So let us see the first polynomial x cube minus 5x plus 10. So the given polynomial is f of x is equals to x cube minus 5x plus 10. So to apply already we know the Einstein criterion. If f of x is a polynomial of degree greater than or equals to 1 and p is a prime number such that p square does not divides a naught, p divides a naught, p divides a1 and so on, p divides an minus 1, but p does not divides an, then the polynomial is irreducible over capital Q. So to apply this Einstein criteria, first you have to compare the given polynomial with f of x is equals to f of x is equals to a naught plus a1x plus a2x square plus a3x cube. So our polynomial in the form 10 minus 5x plus x cube. By comparing one another we get a naught is equals to 10, a1 is equals to minus 5, a2 is equals to 0, a3 is equals to 1. So now choose the prime number p is equals to 5. It is obvious that p divides 10, I mean p is a prime number here. 5 divides 10, it means p divides a naught. 5 divides minus 5, it means p divides a1. 5 divides 0, it means p divides a2. 5 does not divide 1, it means p does not divide a3. And also you observe that 5 does not divide, 5 square does not divide 10. It means p square does not divide a naught. So now you observe that p divides a naught, p divides a1, p divides a2, but p does not divide an and p square does not divide a naught. This shows us the polynomial, the prime p satisfies all the properties of Einstein criterion. Therefore, x square minus 5x plus 10 is irreducible over q. Now let us check one more polynomial. This one, x square minus 3x square plus 9. So the given polynomial is f of x is equals to x power 4 minus 3x square plus 9. To solve this, first you have to compare with the polynomial a naught plus a1x plus a2x square plus a3x cube plus a4x power 4. From this comparison you get a naught is equals to 9, a1 is equals to 0 because there is no x term, a2 is equals to minus 3, a3 is equals to 0, a4 is equals to 1. Now choose the prime number p is equals to 3. Choose the prime number p is equals to 3. Now you check that 3 divides 9. It is clearly p divides a naught. 3 divides 0. It means p divides A1. 3 divides minus 3, it means P divides A2. 3 divides again 0, which means P divides A3. Now check, but 3 does not divides 3 does not divides 1. It means P does not divides A4. Instead of A4 you can write AN also. Excuse me. 3 square at the same time. So from here P square, the prime number 3 square does not divides 9. Actually P square divides 9 here by choosing the prime number P is equals to 3. 3 square does not divides 9. This is wrong. 3 square divides 9. 9 divides 9, which implies P square divides A naught. This condition applies as here in our Einstein criterion. Actually we need to show that P square does not divide A naught, but here P square divides A naught. This condition applies as here it is not possible to apply the Eisenstein criterion for the irreducibility of this polynomial. Check that. So it is not possible to apply the Eisenstein criterion here. Now let us see the next problem. 2x power 5 2x power 5 minus 5x power 4 plus 5. 2x power 5 minus 5x power 4 plus 5. So you have to compare that. A5x power 5 plus A4x power 4 plus A3x cube plus A2x square plus A1x plus A0. So simply you get A0 is equals to 5, A4 is equals to minus 5, A5 is equals to 2. All the other terms, A1 is equals to A2 is equals to A3, they must be equivalent to 0. Now choose the prime number P. Choose the prime number P is equals to 5. So obviously P divides A0 because 5 divides 5, and P divides A4, and P divides even A. P does not divides A5, and P divides all the remaining one. P divides A1, P divides A2, P divides A3 because they are 0. So also P square does not divides A0. Here P square is 5 square. 5 square does not divides. 5 square means 25. 5 square does not divides 5. So here Eisenstein criterion satisfied. Therefore we conclude that by Eisenstein criterion the polynomial 2x power 5 minus 5x power 4 plus 5 is irreducible over capital Q. That's it. Now the next problem, and very important problem, let us see that. Show that pi p of x is equals to 1 plus x square plus and so on x power p minus 1 is irreducible over q, where p is a prime number. Very important problem for examination. So the given polynomial can be written as pi p of x is equals to 1 plus x square plus and so on plus x power p minus 1. Simply this polynomial can be written as 1 minus x power p divided by 1 minus x. 1 minus x power p divided by 1 minus x. Yes, it is right. You can check it. So first you can multiply with 1. 1 into 1 minus x. It can be written as minus plus x minus x power p. Now multiply with x, x minus x square minus plus, you get x square minus x power p. So continue like this. So you get this. So simply this one you get 1 plus x square plus and so on plus x power p minus 1. So pi p of x can be simply written as 1 minus x power p by 1 minus x. Now replace this x by x plus 1. So obviously then becomes pi p of x plus 1 is equals to 1 minus of x plus 1 power p divided by 1 minus of x plus 1. So after simplifying we get 1 minus x plus 1 whole power p divided by minus x. So here you can write like this. By using binomial theorem, it can be written like this. 1 by x into x plus 1 whole power p minus 1. First I rewrite the terms, so that's why we reduce this minus. Now applying binomial theorem, 1 by x into pc naught x power p plus pc1 x power p minus 1 plus pc2 x power p minus 2 plus and so on plus pcp minus 1 x plus pcp minus 1. Everybody knows that NCN is equals to 1. So PCP is equals to 1. 1 minus 1 get cancelled. It becomes 0. Now on dividing with x, everywhere we get PC 0 x power p minus 1. By dividing with x, by dividing this x every term, x power p minus x power p minus 1, x power p minus 2 and so on x, we get simply this. PC0 x power p minus 1 plus PC1 x power p minus 2 plus and so on plus PCP minus 1. So here, now you observe that here P divides all the coefficients. P divides all the coefficients of pi p of x plus 1 except that it divides all the coefficients, but it does not divides the coefficient of x power p plus 1, except that coefficient of x power p plus 1, p minus 1, this one, x power p minus 1. And also because pc0 is equals to 1, so prime number does not divide 1. So except x power p minus 1, and also p square does not divide pcp minus 1, it means the value of p. So here you can apply the Eisenstein criterion to this polynomial. By applying Eisenstein criterion, pi p of x plus 1 is irreducible over q. If pi p of x plus 1 is irreducible over q, then obviously pi p of x is also irreducible over capital Q. This completes the solution of our problem. And remember that this problem is very, very important to examination also. So there is an important note point. Pi p of x is irreducible over q, implies and implied by pi p of x plus 1 is irreducible over q. Let us go for next problem. Show that x cube plus 3x plus 2 belongs to Z7 of x is irreducible over the field Z7. Yes, Z7 means is consists of elements 0, 1, 2, and so on up to 6. Z7 with respect to addition modulo 7 and multiplication modulo 7 is clearly a field because this 7 is a prime number. So now our polynomial is given like this. F of x is equals to x cube plus 3x plus 2. What is f of 0? 2. Does not divisible by 7. What is f of 1? 1 plus 3 plus 2, which is equivalent to 6, not divided by 7. Similarly, you can check every number. F of 2 is equals to 2 cube plus 6 plus 2. 8 plus 8, 16, not divisible by 7. f of 3 is equals to f of 3 is equals to 3 cube plus 3 into 3 plus 2. 27, 36, 38, not divisible by 7. Similarly, f of 5, f of 6, f of 4 are also not divisible by 7. If they are not divisible by 7, it means in Z7 there are no roots for that polynomials. You can check it. For example, f of 6. What is f of 6 here? F of 6 is equals to 6 cube plus 3x. 3 into 6 plus 3 into 6 plus the polynomial is plus 2. Plus 2. What is 6 cube? 216. 216 plus 6 3s are 18 plus 216 plus 18 plus 2. What you get? 236. 236 does not divisible by 7. 236 is not divisible by 7. So the remainder is not a 0. So f of 6 is not equals to 0. Similarly, we show that f of 1, f of 2, f of 3 all are not equals to 0. These numbers all are not equals to 0. It means the polynomial has no root in Z7. It means f of x is irreducible over Z. F of x is irreducible over Z. So right, we solve next problem by using one more theorem. Let us see the problem. Show that x cube minus x minus 1 belongs to capital Q of x is irreducible over Q. Here f of x is equals to x cube minus x minus 1. Suppose f of x is reducible over Q. Actually, you have to show that irreducible. Assume that it is reducible over Q. By using the theorem, if f of x is a polynomial of degree 2 or 3, then f of x is reducible over f if f of x has a root in capital F. Therefore, we assume that f of x is reducible, so f of x has a root in Q. Here, all the coefficients of f are integers. Therefore, f of x belongs to z of x. Also, the leading coefficient is 1. The coefficient of x cube is 1 here. The coefficient of x cube is 1. It means the polynomial f of x is monic polynomial. If f of x has a root small a belongs to q, then a belongs to z and a divides a naught. What is here a naught? A naught is equals to minus 1 in our polynomial. It is. Here it is. A naught is minus 1 in our polynomial. A naught is equals to minus 1. And by applying that previous theorem, this one, a divides a naught. A divides a naught means a divides minus 1. So a divides minus 1 means a is equals to either plus 1 or minus 1. Therefore, plus 1 or minus 1 is a root for f of x. Now check that whether it is root or not. What is f of 1? 1 minus 1 not equals to 0. What is f of minus 1? Minus 1 plus 1 minus 1 not equals to 0. It means f of x, it means plus or minus 1 is not a root of f of x. So f of x is not irreducible. It means f of x is irreducible over q. This condition exists because of our assumption f of x is reducible over q. I repeat this problem. This is a different theorem, different application of one theorem. Already we learned this. If f of x is a polynomial of degree 2 or 3, then f of x is reducible over f if f of x has a root in f. We are applying that theorem here. In our polynomial, here x cube minus x minus 1 belongs to q of x. All coefficients are integers. Therefore, the polynomial belongs to z of x. And also leading coefficient is 1. So, f of x is monic polynomial. Our assumption is f of x has a root small a belongs to q. Then a belongs to z and that a divides a naught. So, here a naught is minus 1. A divides a naught means that a has two values plus or minus 1. But you check that plus or minus 1 does not satisfy this polynomial. Plus or minus 1 does not satisfy the given polynomial. It means they are not roots for the given polynomial. It means f of x is not reducible. So f of x is irreducible. So in the next video, we'll learn the adjunction of roots and some. The next topic is adjunction of root. We'll learn extension fields, degree of the extension field, and some theorems. Keep learning. Wish you all the best.